to it.
Oh, you're using his phone?
Yeah, well, you're on flash now.
Go ahead. 100 years ago, if you were to tell someone that every day a little black box that glows and is made of mystical metal components, and you can look anything up that you want to, and it'll give you back a result, and you can talk to anybody across the world, they would burn you for witchcraft. I've spent the last 10 years of my life trying to understand how these magical boxes, computers, work. I've done this both personally, professionally, and academically. And I've noticed that many people in our day and age don't understand computers much better than a person 100 years ago would. So today, I'm going to try to help unveil the mystery of what a computer is using what I consider to be the most important part of the computing tech stack, which is compilers. What they are and how they work. So, let's begin. What is a compiler? A compiler is something that takes one type of code and then converts it into another type of code. Generally, most code is run on a computer, and computers run using ones and zeros. But how does a computer actually run those ones and zeros? On a computer, you have an item called a chip, and the chip is wired up very similarly to a house, and that's why they call it computer architecture. And on that chip, they have a set of logic that will occur, which, when powered, will have a set of instructions that will occur. And we call this a basic programming language, and this is called the computer's machine code. This machine code, humans can't really understand. So what we try to do instead is write an assembly, which is just machine code, but transcompiled, so it looks visible to us, but it represents the same exact things. If we look at the number of projects that are written in assembly, it's 0.1%, which means the other 99.9% of code are compiled. So, code is compiled. How does a compiler work? So a compiler takes one type of code and turns it into another, and it does this by a system of rules and procedures that it follows, and has a very set logical pattern that it occurs to. It's an old adage that compilers work. If you lie to a compiler, it will get its revenge. Now, compilers have three main steps, as shown here. There's parsing, abstract syntax tree, and code generation. Parsing occurs where it takes whatever meaningful and important parts of the code and it turns them into little blocks. In the abstract syntax tree, those little blocks get assigned to how we think of math and code, and it builds those relationships back up together. In the code generation, it takes that abstract syntax tree and it generates that into a final outputted code. Generally, this would be machine code. So, if we were to look at this example, a is equal to 4 plus 2. As humans, we would go, okay, we need to solve for a, 4 plus 2, that's 6, a equals 6. We want our compiler to do the exact same thing and turn this into something that a computer can understand. So, we're going to start with the first step, which is parsing. We're going to start with a. We're going to add this to a list of tokens. Those tokens represent each of those chunks. So a is a variable, that's something that can change. Following a variable, we always want to have either the end of a statement or an assignment. And we can see this equal sign is called an assignment. So that means that we're definitely going to be assigning something to a, or 6 in the end, but we're not there yet. The next token is 4. This is a value, which is just a number. Then we have our plus sign, which is an operator. An operator can be plus, subtract, minus, divide, anything else too. We have another value, which is 2, and then we have the semicolon, which represents the end of the line. Now that we have taken all of our token and abstracted this written code into an idea, we can start putting it together. So we're going to start with the first token, which is a variable, a. And after a variable, we can either have the end of the line or we can have an assignment. So we check the next token. It's an assignment. So we make the assignment its child to the right, and the right is checked after the left when we're doing our code generation. Then we check our assignment. Our assignment needs a value, so we check the next thing is a value. So we add a value to the side. The reason why we add it to the side is because we check what's after our value, because it's an operator. After a value can be an end of the line or an operator. In this case, it's an operator. So we're going to wait. Because it's an operator and the 4 is used in the operation, we make it the child of the operator. Then we check the next token. That's a value. We add that as the child to the operator. We check the next value. This could be an operator or it could be end of line. In this case, it's an end of line. So we add that back to the main tree and we add the end of line. Finally, we're going into the code generation step of the compiler, where we're going to be processing through this tree to develop our final machine code, or in this case, assembly. So we start at the top, our A. This is a variable, so we tell the computer with this code that we're going to create a variable. Then we go to our assignment. our assignment requires a variable, or requires a value, but we don't have a value yet. So we're going to put a pin in this, and the computer's going to figure out other stuff before figuring out what that value is. So we're going to go to check the left. There's nothing on the left. We check the right. The right is an operator. The operator isn't a value, but an operator will always yield a value. So we know that we must check left and right. So we check the left. That's a 4. We check the left and right of that. There's nothing, which means this is a true value, and we assign that into memory. Then we check the right child of the operator, and that's the 2. We assign that into memory as well, and we see that on the right side of the 2 is the end, which means that we can finally yield our operation, which is the plus and minus. So, which is the plus. So 4 plus 2 gets computed into memory, and then finally we know our value, so it can get assigned to the A. And that occurs, and this is our completed code. All compilers work in this manner. They compile some abstract idea into a simpler idea, and then re-represent that in some code. Now, there are other types of compilers. There's just-in-time compilers and image compilers and many other types of compilers. But a real-world example of this would be your browser, which uses both image compilers, pre-compiled code, and just-in-time compiled code. So when you boot up your browser, that's a pre-compiled project, and that code will run. And when you look something up, it'll make a request to Google, which will return HTML, CSS, and JavaScript. The HTML and CSS will be rendered into a physical image, which will then be shown through the machine code onto your screen. The JavaScript, which is your interactions, will be shown onto the screen, and your interactions will be available because as you're interacting with where the JavaScript gets activated, it gets compiled and run just in time. So as you click, it compiles and runs it right away. To re-summarize, I've gone over what computers understand as code, how that code is generated, and how the generation of that code occurs. I hope that going through all these steps has made the process of understanding computers a little bit less obscure and more easily accessible. And if you get sent back into the past 100 years somehow, you'll be able to talk your way off that executioner stand. Thank you very much. Oh.
I was trying so hard not to laugh, like, and let's begin. Click, and it's a right click.
No, it's